for fun, we have Sivakanth. He's a senior researcher in the algorithm based upon research that he received a PhD in 2000 from Princeton. Interest in theory and differential privacy. And we're very glad to have him here in person today. And he's a private convex optimization via exponential mechanics.
Thank you for the invitation. It's been a while since I've given in-person talk, so there might be some hiccups with this hybrid meeting. So please excuse us. And can you all hear? Can you hear us really fine? Right now? Yeah. Okay. Great. So let me start. So this is a joint work with Yintat Lee from. Is there an echo? Do you hear an echo, or is this fine? Okay, so this is joint work with Yintat Lee, and it's sorry, just a moment. Might be.
Sivakanth?
Yes.
I'm Adam. Nice to meet you in person. Sorry.
So yeah, this is joint work with Yintat Lee. Yeah. You're not seeing my screen? Yes, this is joint work with Yintat Lee from UW and the student Dao Gao. So yeah, so we often want to do private machine learning or machine learning on private data. So we collect data from users. So this is private data. So we collect Y1, Z1. This is like input-output pairs from users, and we want to train a machine learning model, which does correct predictions based on these examples. So we typically minimize the loss functions. We have a model, and we minimize the loss function, which is the average of the losses that this model sees across these examples, and then we find the best model. And we want to do this in a privacy-preserving way. So we want to do this in a privacy-preserving way, which is we want to train this model while preserving user privacy. And in many cases, the loss function is convex in the parameters W. So we study differentially private. The lag is quite
It's fine on my end.
Okay, I think, yeah, for the people who are remotely coming in, it's fine, but people who are in person, there's a lag. But,
You could look at your computer.
yeah, maybe that's. It's harder.
The lag should be this. They're all on Zoom, right?
It's the screen itself.
It's the screen, so.
It's like
Oh.
TV screen.
Oh, I see. I
Here.
see. Oh, that's weird.
Yeah.
I think very often it's open, it's trying to airdrop.
I see.
And it's just, I think there is a lag.
Got it.
Sorry about that. So yeah, so, but can you see this?
Yeah, we'll just watch on.
Okay. Sorry, it's too small. I can make it bigger somehow.
No, it's fine. I think it's just you know.
Okay. All right, sorry. So yeah, so we want to minimize a convex function over some convex domain, which is bounded. And so typically so we have this loss functions for each user, this fx sub I. So the SI is the data that private data that the user SI gives. And then we want to minimize the average loss. So, and we are assuming that this fxs is convex in X for every fixed value. Okay, so to be more precise, the goal is to design a differentially private DP algorithm to output a private output, which is X private, which approximately minimizes the loss function, the average loss function. And in this talk, I'll assume that D and D prime are neighboring data sets, mean that they differ in the data of a single user. So they both still have size n, but they differ in a single user, let's say SI and SI prime. Okay, that's the notion of neighboring data sets. And we want to get an epsilon delta DPL. Okay, to be even more precise, what does it mean to approximately minimize FXD? So we want to minimize the excess empirical risk. We want to minimize the excess empirical risk, which is the difference between the expected value of the function on the output of the algorithm minus fx star b. I guess this is flagging, but this is fine.
Yeah, we're
okay.
good.
So I'll just go with this.
Yeah, just
Yeah,
go. Don't worry
So,
about
yeah,
it.
so we want to minimize the excess empirical risk, which is what is the expected value of the loss function minus on the output that our algorithm gave minus what is the true minimizer of fxd, which is fx star d. Okay, so this is the excess empirical risk, and we want to minimize this. So, and one way to solve this is by the exponential mechanism. This is one of the first mechanisms invented in DP, but this is by McSherry and Talvar in 2007. And you can use this to solve this empirical risk minimization problem. So the algorithm is quite simple. You sample from this density, which is the exponential in minus k times the loss function, which is the average loss function. And you can sort of imagine why this is private, because, so firstly, you're not, you're spreading the distribution over many possible minimizers and not the exact minimizer. And so you can imagine, you can kind of intuitively see that when k is large, it kind of samples a good minimizer, but then it's not really private. And when k is small, you're spreading your distribution over a large space, so it's kind of private, but it's not really good. It's not finding a good minimizer. And by choosing the good k, you can get optimal or good privacy utility trade-offs. So if delta is the sensitivity of this function, which is like let's say little f's are bounded, then delta is the bound on this little f's, which is let's say they're bounded between 0 and 1, then delta is 2. Then choosing this k to be epsilon over delta, you get epsilon 0 differential privacy, which is the pure differential privacy. And it's also very easy to prove because you can just look at the ratio of these densities, the ratio of two such densities. And if little f is bounded, then the ratio of the density is also bounded. So it's quite simple to prove that this is epsilon delta differentially private. And you can also show that this thing achieves good utility. As I just said, if you choose larger k, you should get good privacy. So you can show that the empirical risk that is achieved by this algorithm is d or n epsilon times the sensitivity. So what we need to see from this is that if to get good excess empirical risk, which is to make this little 1, what you need to do is choose n to be much, much bigger than d. So you need to have, like in high dimensions, you need to have a lot of users for this algorithm to work well. Okay, which is kind of a problem is in high dimensions, especially because we will not have so many users. But the good thing is that this works even if little f is not even convex. We never use convexity. All we need is that these loss functions are just bounded. Okay, so this is the exponential mechanism. Okay, so as I said, we want to do better with this linear dependence on d. The fact that n should be much, much bigger than d for it to make sense is kind of a problem. So we want to do better. So we will assume a little more about these loss functions. As I said, we will assume that f is convex in x. But we'll also assume that they are Lipschitz. So what G-Lipschitz, what that means is that the gradient norms are bounded by G, okay? And we are not assuming any smoothness of the loss functions. Okay, so and then we also assume that the domain is bounded and convex. Okay, so these are the assumptions. The main assumptions are the convexity and the fact that these loss functions are G-Lipschitz, which is the norms of the gradients of the loss functions are bounded. Okay, under these mild assumptions, we can do much better. So we just discussed the exponential mechanism achieves d over n loss. And Basili, Adam Smith, and Takurta, they showed that you can do much better, under these assumptions. And if you relax the privacy to approximate differential privacy, which is epsilon delta, you can get square root b over n. So this is a huge improvement. This is like a square root b improvement. And now we just need the number of users to be much bigger than square root b. It's now more reasonable. We can actually use this algorithm in high dimensional settings. So yeah, this is a big improvement. And these papers also showed that these bounds are optimal. Like under this notions of privacy, this is the best empirical risk, excess empirical risk that you can get. Any questions so far?
Just because it's hard to see the bound. Okay. So the bound from Smith and Takurta, is that via the exponential mechanism or
no? So it's a notion. It's a variant of It's a variant of noisy gradient descent. So using that, you could get this optimal excess. Okay, and then there are subsequent things which improve the running time or things like that. So, but the optimal excess empirical risk is this. Okay, so and for simplicity, I stated all the bounds in the small epsilon regime, where epsilon is much smaller than log 1 or delta. In the large epsilon regime, the bounds are different. You'll get 1 over square root epsilon instead of 1 over epsilon. But so that's in this talk, I'll only talk about the small epsilon regime. Okay, so and to be to remind people of what this noisy gradient descent is, it's basically like you take the gradient of the function. So in normal gradient descent, you take a descent step in the negative gradient direction. But now you add some noise, Gaussian noise to the gradient, and then take a step in the direction. Okay, and you can also do a stochastic version of this, where instead of doing the gradient, compute the gradient on the entire loss function, which is the entire empirical loss, you sample a small subset of the database, and then you only compute the gradient with the subset of things. And this has some nicer privacy properties. You get privacy amplification due to sampling, subsampling, and that improves the privacy properties. So often this stochastic gradient descent is used in this algorithm. Okay, so there is also a related problem, which is DP stochastic convex optimization, which is, here we assume that the loss function is the expected loss over some unknown distribution of users. So, so there is an unknown distribution which is underlying, and we don't know what this distribution is. What we are given is n samples from this unknown distribution. So that we sample some n users at random, and we only get these n samples. And from this, we want to output a minimizer to the true loss function, which is really unknown to us. What we have is access to samples, and we want to minimize the excess population loss, which is the expected value of the true loss f tilde at the output that we gave minus the f tilde at the true minimizer. Okay. This is excess population loss. You see, this is slightly different. So the expectation is also over the database that we sampled of end users here. So this is harder problem than empirical risk minimization. And but even here we know how to get optimal bounds. So in papers by Basili et al. And Feldman et al., they showed that you can achieve the optimal excess population loss. In this case, the excess population loss has two terms. So this term, which we have already seen, is the right term is due to the privacy. This is the DPER, and this is the same bound that we got for optimal the optimal excess empirical risk. The first bound, which is GD by square root n, has nothing to do with privacy. It's just the generalization gap. The fact that we are only seeing n samples out of an infinite population inherently introduces some error, and the first term is just that. And the second term is due to privacy, and this is optimal bound, and we can achieve it. Okay, so all good. So what is it completely solved? So what is unsatisfactory about this situation? So firstly, the variant, especially for DPSCO, this is stochastic convex optimization, the variants of noisy gradient descent which achieve this bound are quite complicated. So it's not just a simple noisy gradient descent. You may then have to smooth the function using some complicated things and then do gradient descent on that, or there is some other techniques. called like iterative localization, which achieves these bounds. Moreover, the same algorithm doesn't work for both DPRM and DPSCO. So in general, it's DPRM is like easier, but DPSCO you need to add some extra things to to really achieve these things. And because of this complicated analysis, the constants in the privacy bounds or the utility bounds are quite large because of this large, complicated nature of these algorithms and the number of steps involved. So let's. So what is our contribution? So our main theorem is that you can have a simple modification of the exponential mechanism, which actually achieves optimal bounds for both DPRM and DPSCO. And moreover, the privacy bounds that we prove are exactly optimal. There is not even loss in constants. And the bounds that you get for the excess empirical risk and the excess population loss are also really clean and simple, as you will see. There are no hidden constants, or the constants, if at all they appear, are really small, like 2. And more, there's a clean separation between the privacy bounds and the utility analysis. So if there is I'll just explain what this means. And we also show how to implement this modified exponential mechanism efficiently. Okay, so these are the main contributions. Any questions so far?
So when you say optimal with no hidden constants, you mean like 1 plus little o of 1 optimal? Or
so the privacy bounds? Yeah, they are not. No, it's like the exact. There is no little o either. So
Maybe a related question. Optimally with respect to what class of mechanisms, pure DP mechanisms?
Epsilon delta. No, not even epsilon delta. Okay, so what I mean is optimal privacy bounds means that with this mechanism, you cannot improve the privacy analysis.
So like optimal with respect to this mechanism. I see.
Sorry.
Like sort of like tight for this
Yeah,
particular
for this mechanism, you cannot improve anything. Yeah, because it's hard to. We don't even know how optimal lower bounds like. So it's
that was where my question was
yes.
coming.
So we don't know the constants in the optimal lower bounds. Okay. Any other questions? Or I'll go into the modification of the new mechanism. So we call it the regularized exponential mechanism. So, and it's quite simple. You sample from, instead of the loss, e to the minus k times loss function, you add an L2 squared regularizer. So you just sample from exponential in minus k, f of xd plus mu times the L2 norm x squared by 2. So it's come out now. So you just added, a L2 squared regularizer to the loss function, and you just sample from the exponential mechanism. So that's it. That is the mechanism. We give efficient way to do this, and we also show that this achieves optimal SCO and DPRM bounds just by choosing the optimal k. So yeah. So for example, for DPERM, you can do this using n-square queries to the values of f. So we are not using gradient queries, we are just using value queries. And you can do it using n-square queries. And for DPSCO, you can do this sampling using n times min of n and d queries. And you can achieve the optimal bounds, optimal excess empirical risk and optimal excess population loss. So we also prove a matching lower bound, saying that for DPSCO, that if you only have value queries to f, these are the minimum number of queries you need to achieve this. Okay, so
potentially, if you had like gradient queries.
Yeah, so that's a really good question. So at least our conjecture is that using gradient queries, you only need n instead of n times d.
And there are algorithms that come close to that, aren't there?
So right, so the algorithm which achieves n gradient queries requires smoothness of f.
I see.
Whereas here you're not really showing any conditions on f.
Right, that makes sense.
Yeah, so without smoothness, the best previous bounds, I'll show that at the end, they're quite complicated. They're like n square, n to the something times d to the something. So they're a plethora of these things, but there is no n. Okay, if there are no questions, I'll go into the privacy analysis, which I think is very interesting. Okay, so for the privacy analysis, we'll need the notion of trade-off curves. So instead of the usual epsilon delta, there is another way to characterize the privacy of an algorithm, which is the notion of a trade-off curve. So in the usual epsilon delta definition, an algorithm does not satisfy a fixed epsilon delta. It's like for every epsilon, there is a delta for which it is epsilon delta differential private. So you can combine all these guarantees into a privacy curve, which is a delta as a function of epsilon, and that is given by this at the top. It is it's just a function of epsilon. You get supremum or all subsets, probability of y in S minus e to the epsilon times probability of x in S. So this is the usual privacy curve. But there's a different way to characterize privacy, which is you fix this term on the right, which is you fix probability of x in S to be some constant here in this case minus z, and then you ask what is the minimum value of probability of y in S. This is a trade-off curve. And just by convex duality, these are just equivalent. One is in fact the convex dual of the other. So it's just an equivalent way, but somehow it's easier for us to work with trade-off curves.
Yeah. Is there a reason you want to look at the kind of end of the spectrum? It's, I guess, equivalent to look at the small probability. This is looking at sort of large probability events. Like you're saying,
this is 1 minus z.
Because of the 1 minus.
It's just an artifact of how people defined it. I personally think we should have defined it as z. I just went to this definition because when they first defined this, they defined it in this way. But intuitively, it makes more sense to just put it as z there. But
it's just the the same curve but sliced a different.
Yeah, exactly.
And you actually need convex duality to prove those are equivalent.
Yeah. You can get one from the other. Okay. So anyway, so the important part that we need is the fact that to compare two privacy curves, it's enough to compare the trade-off curves and the order reverses, which is because of the convex duality. So if the privacy curve between P and Q is less than P prime Q prime, if only the trade-off curves follow the opposite order. So in the same paper where they define this trade-off curves and this thing, they define the paper is actually called Gaussian Differential Privacy, and then defined yet another notion of privacy, which is just a simple way to compare the privacy curve of a mechanism. So they somehow said that let's look at the privacy curve or the trade-off curve of a Gaussian mechanism, which is I'm comparing N01 and N1. So this is a Gaussian mechanism whose noise scale is 1 and the sensitivity is 2. So that is the privacy curve of this Gaussian mechanism. And they somehow made this a symbol for this, which is G mu. And they decided that let's compare all privacy curves to those of a corresponding Gaussian mechanism. So it's just a simple way to compare privacy curves, because as we said, privacy curve is a one-dimensional function. So it's hard to characterize a one-dimensional function like single number. So they said, okay, let's assume what is the equivalent Gaussian mechanism with at least so much privacy. So that is the Gaussian differential privacy. So we say that a mechanism satisfies mu GDP or mu Gaussian differential privacy if its privacy curve or the trade-off curve is at least that of a Gaussian with parameter mu. Okay, so it's just a simple way to compare things, and the other reason that this is nice is that this guarantee composes very well. If you have several algorithms with different mu GDPs, you can combine them if without losslessly into a single GDP. Okay. So our main theorem is the following. We show that this regularized exponential mechanism satisfies a Gaussian differential privacy where the parameter is g over square root mu. So here you look at P is the exponential mechanism where you sample from e to the minus f of x, and Q samples from e to the minus f tilde of x, and f and f tilde are mu strongly convex, and f tilde minus f is G Lipschitz. Then the trade-off curve between P and Q is at least that of a Gaussian mechanism with parameter G over square.
So here, F and F, F is what you were previously calling like F plus mu squared.
Yeah,
X.
exactly. Yeah, so I already absorbed the mu strongly convex part into that.
And is there something? So, I guess the point is there's nothing special about that regularizer. Like this just works.
Yeah, this just works with any mu strongly convex. So this is the main privacy theorem, and this is also tight. Why is this tight? It includes the privacy of Gaussian mechanism as a special case. So if you let F to be norm of x squared by 2 sigma square and F tilde to be norm of x minus a squared by 2 sigma square, then these are both mu strongly convex, and P in this case is just the Gaussian distribution, right? Because if you're sampling from e to the minus norm of x squared by 2 sigma square. So P is a Gaussian distribution, Q is a Gaussian distribution. And then you can compute, and F tilde minus F is also Lipschitz, where the Lipschitz constant G is norm of A by sigma square. And yeah, as I just said, F tilde are strongly convex. So you can compute the privacy curve between P and Q exactly because it's just a Gaussian mechanism, and it exactly matches the lower bound. Okay, so this is the sense in which I said this is an optimal privacy bound in this case. Any questions?
F tilde, the loss when like the expectation is also over the choice of the data set.
Oh, sorry. No, this is just still ERM. It is not. This is just an abstract theorem. This is.
What's F tilde?
So these are just two things. So you should think of F here as F of xd, and the other F tilde as fxd prime. As also, I'm also adding the regularizer here. So if you look at the difference, that will be G Lipschitz. Actually, G by N Lipschitz. Okay. So there's actually some prior work which actually asked the same question, which is proving the privacy bounds in the special when you add this regularizer. So they actually looked at a slightly different thing where the underlying distribution itself is strongly log-concave. But basically, from their paper, you can get this following privacy bound here, but this is not tight. Like they use log sub inequality to get this bound. And I plotted the bounds that they get was we get here. So the top curve is the privacy bound they could prove, versus the blue curve is the time bound. There's like maybe a factor of 2 to 3 off in absolute.
So like a fixed. It's delta's on that.
Yeah, delta is on it. For small delta, the gap is for large delta, the gap is infinite. For small delta, it's about factor of 2. Okay, so let's show. I'll show the proof of privacy. So the proof of privacy uses this isoperimetric inequality for strongly log-concave measures. So I just wrote down the theorem here, but let me just explain it in pictures. So I have some pi, which is the mu strongly log-concave measure. What it means is pi of x, the density, is proportional to e to the minus f of x, and f is mu strongly convex. That's what it means to be strongly log-concave. And so there is this measure, and I have some subset A, whose measure is some constancy. Now I ask, what happens if I take a neighborhood of A, let's call this AR, where I look at all points of distance at most R from A, so which is including A. AR is this whole set. And I ask how much the measure of A, what is the minimum value amount in which the measure of AR should increase? Like, so this is some notion of expansion. It's like, it should at least expand this much. So that is the bound that we want to prove. So we want to say that it is, so what this bound is saying is that it should at least expand by this much. So what is this mysterious expression on the right? this here phi is the Gaussian CDF. So why does this mysterious expression come? So this expression comes just by taking, so what is really saying is that the worst case for this thing, what is the minimum amount of growth of AR in measure? It happens when pi is a Gaussian distribution, with appropriate points, and A pi is Gaussian, and A is a half space. So this is the worst case. So and that's how you get the bound on the right. So it should grow by at least as much as a Gaussian grows when A is a half space with measure exactly Z. So yeah, in that sense, it's an isoperimetric because when R is small, it is basically about the perimeter of A. But when the limit when R tends to 0, it characterizes the perimeter, the surface area.
Sorry, what's the relation to surface area?
So when R is really small,
yeah,
this AR, the volume of AR minus volume of A
is the
the surface area.
Take the limit as R goes to 0 over R D or something, over
R to the D minus 1.
You get the surface area, and that's okay.
So using this, you can prove type concentration bounds for Lipschitz functions. I will not go into how you prove it. It's a very simple proof from the from the isoperimetric inequality. What you can show is that if you have Lipschitz function, the probability that it takes a value more than constant, this mz is basically the z median, which is the probability that it takes a value greater than mz is exactly z. Then what is the probability that it takes mz plus r? You can get a tight concentration bound on this. So you should just think of it as a concentration bound for Lipschitz functions, but this is like really tight, and it comes from the isoperimetric. Okay, so
a question: is this like the intended use of that isoperimetric inequality? Is this like this? Was this in that original paper, or?
Yes, I think this is pretty standard. This is a pretty standard use of isoperimetric inequality to get concentration bounds for Lipschitz functions.
Cool.
Yeah.
And could you get?
So I mean, I can give you a rough idea of the proof. So basically, so what we are saying, let's say A is the set of X such that alpha of X is less than or equal to M of Z. And where we chose M of G such that the measure pi of A is exactly Z. That is just the definition of MZ. We chose the median, the Z median. So if Z is half, then M of Z is just M of half is just the median of this distribution. Okay, of the distribution of alpha. When X is sampled from pi. Okay.
So it's like a level.
Yeah, it's like
alpha. I lost track of what alpha is.
So alpha is some G Lipschitz function, and we are sampling X from pi, which is a strongly log-concave measure, and we want to understand the distribution of alpha.
They're not necessarily each other. Alpha and pi are not
tied to each other. No, alpha is any G Lipschitz function, and we want to understand how concentrated is the distribution of alpha itself.
I should think of alpha as like the log odds ratio.
Yeah, you should think of it as log odds ratio in our case, yes. So, and the proof is, as I said, so you take A to be this. And now if we look at AR, which is the set of all points which are far away. So, if for alpha to be greater than mz plus r, it should be far away from this set A because alpha is G Lipschitz. So the set of points where alpha of X is at least mz plus r are all far away from this set A, and isoperimetric inequality gives an upper bound on all the far away points. So that's how you get this. It's a pretty straightforward application of isoperimetric.
It's tight for like the Gaussian mechanism.
Yeah, and it's tight for a Gaussian.
Gaussian mechanism, alpha is really a linear function, so it's like corresponds to half space.
Exactly. Okay, so now let's see how we prove the privacy bound. So I'll assume that G and mu are 1 for simplicity. Otherwise, there's many floating parameters. And our goal is to prove that TPQ is at least T n 0, 1 and n1, 1, the trade-off curve between Gaussian and shifted Gaussian. So let me remind you that P is a proportion, is a density proportional to e to the f of minus x, minus f of x, and Q is proportional to e to the minus f tilde of x. Okay, so let's assume, let's denote the difference between f and f by alpha. So we know that this is a Regularized function, alpha, which is the difference function, and q of x. Now I can rewrite it as proportional to e to the minus alpha x times p of x, just by the definition. Okay, so now I want to calculate the trade-off function TPQ of z. So by definition, this is the infimum or all sets whose measure under P is 1 minus z. And I want to minimize that. So I'm fixing the measure of P to be 1 minus z, some constant, and then I'm minimizing the measure of Q. So what is the set which minimizes this? So I have a fixed measure of P. I want to minimize the measure of Q. So I should choose those points where the ratio is as small as possible. The ratio of the densities is as small as possible, right? So I should look at all the points where the ratio of density of Q and P is as small as possible, and then choose all those points until I get a measure of 1 minus z for P. So that is the set S, so which is a set of all x where Qx by Px is less than some threshold. And this threshold is chosen such that P of S is 1 minus z. So this is just same as set of all x such that alpha of x is at least some threshold m of z. Okay, so now I can calculate TPQ for this set. Basically, it's just the measure of Q for this specific set that I chose. And after some simplification, you can rewrite it like this. And we want to lower bound TPQ. So to lower bound TPQ, it's enough to lower bound this term, which is the expected value of P e to the minus alpha times the indicator function of the set S, and upper bound this set. This term, which is the expected value of P e to the minus alpha times indicator function of S complement. So, even if you don't follow the proof exactly, I just wanted to give you a flavor of the proof, how the argument works. So far, it's pretty straightforward. There is nothing, everything is an equality. There is nothing magical happening. Okay, so now we want to lower bound this term, the expected value of P e to the minus alpha times the indicator function of set S. And as we said, S is the set of all x such that alpha x is greater than or equal to mc. So it's just the integral of this quantity where x ranges over points where alpha x is at least mc. So you do some integration by parts, and you can rewrite it like this, where on the right you get this tail bound on alpha x. Then again, this is an exact equality, so it's just there is no inequalities or magic happening. So I'm rewriting to get a integral on the tail bound on alpha. Now I use the tail bound on alpha that I derived using isoperimetric inequality. And then I just do integration by parts again, and I can compute this quantity exactly. Okay, so I get some bound, and I do the same thing for the other term. I do integration by parts to get the tail bound here. And then I use isoperimetric inequality to say this should be a plus. So I'll get the tail bound, and then I use the isoperimetric inequality to get the tie tail bound. And then I do integration of parts again, I get some closed form expression here. So, and then I just combine. So these are the bounds that we showed so far. And now we just combine. So this is the TPQ expression that I derived, and I plug them in. And then I get this thing. And then, the numerator plus denominator sum to 1. So I get this simple bound here. And this is exactly the trade-off curve between two normals. So the proof just falls in place once you have the right ingredients and use the isoperimetric. So everywhere we use the tight inequalities, that's why we never lost anything. And this is why the privacy proof is tight for Gaussian. Okay, any questions about the proof? Okay, so let me get into the, so now we've seen that it's private. Now let's see what is the utility of this algorithm. So why it gives good bounds, good utility bounds. So for ERM, so there's this simple theorem that if you sample from e to the minus k of x minus exponentially minus k times f of x, then this is the excess empirical risk is upper bounded by d over k. So, and this is true for any convex function f. So therefore, in our case, the excess empirical risk is d over k, because we added a regularizer, which is an error that we introduced. So we're not really minimizing f, but f plus the regularizer. So therefore, we get an extra error. So this is the d by k, which comes from the above theorem, and we get an extra mu d squared by 2, which is due to the regularizer. And the privacy bound that we prove implies that to get epsilon delta differential privacy, you need to choose k like this. And so I plug in this k into this bound here, and this is the bound I get. And I chose the best mu, which minimizes this, and I get the optimal excess empirical risk.
The utility guarantee, what's the citation there? DKL?
Not entirely sure. Yeah, but it's some paper which talks about sampling from these distributions. I think.
I just want, it looks very similar to the analysis that appeared in the privacy papers before that.
Yeah, I think we cited this because it gives the type constant. That's the only right. So that constant is just one.
D was the diameter.
Yeah, the diameter of
the
So yeah, so because we added this extra regularizer that because the diameter is d, the norm of x is that. So the error is this mu. Okay, so it's pretty simple to get the optimal excess empirical risk bound.
Do you need capital D? Like, does the mechanism make sense over like the Gaussian mechanism sort of?
Right, it does make sense. So,
well, I guess, okay, never mind. You know what?
You're right. So if your functions themselves are strongly convex, you don't lose this. Right. So that's what happens for Gaussian mechanisms, because the functions are strongly convex, you don't have this bad dependence on D. So yeah, if you're strongly convex, so this is the bound that we get. This left term here, this is the bound that we get, and there is no extra extent.
It started with the loss function that is already regularized.
Right. Then yeah, then you don't have this extra term, and that left term is the yeah, that's also tight. Okay, so let's come to the utility analysis for DPSCO. So here we will use the log sublevel of inequality for the strongly log-concave measure. So it says that if you have if mu is strongly log-concave and G is any function, I look at G squared, which is a positive function, and I look at the entropy of G. So let's think about it in one dimensions. So G is some function which looks like this, or maybe G squared is a positive part of it. So the entropy is, so if G squared is a constant function, the entropy is 0. And if G squared varies a lot, then the entropy is high. So what we're saying is that the entropy is upper bounded by the expected value of the gradient square, the gradient norm squared. Which means that if your function is jumping a lot around, and so its entropy is high, it can only happen if you're, on average, the gradient of your function is also large. Okay, so it's a very reasonable inequality. This is called the log sublevel inequality. And using this, we can get the following theorem or following lemma to bound the KL divergence between two distributions. So pi is this e to the minus kf, and mu is e to the minus kf tilde, and f minus f tilde are G Lipschitz again. So we want to get the KL, bound the KL divergence between these two distributions. Okay. So, these are our distributions that we are sampling from, and we want to say they are close. So I guess I'll skip the proof in the interest of time, but it's a straightforward application of the log subloop inequality. And you can get that the KL divergence between these distributions is bounded. Okay. And we want to convert this KL divergence bound into a bound on the Wasserstein distance. So what is the Wasserstein distance? It is, you look at all couplings between, so you have two distributions, mu and pi. The Wasserstein distance is, you look at all couplings. Couplings are product, are joint distributions such as the marginals match. You look at all couplings, and then you minimize the expected value of norm of the distance between x1 minus x2 squared. Okay, so this is the optimal coupling in the sense that, it minimizes this the expected value of x1 minus x2 squared. There is also an alternative way to see it using optimal transport, which is like this optimal transport map, which minimizes the L2 distance squared mode. But anyway, so this definition is more useful for us. It is the optimal coupling which minimizes this expected value. Okay, so and what this about bound tells you is it's called the Talagram transportation inequality. What it tells you is that you can bound this Wasserstein to distance in terms of the KL divergence. In case if mu and pi, or at least pi satisfies, pi is strongly log-concave, for example, then you can upper bound the Wasserstein to distance between mu and pi by some constant times square root of the KL divergence between them. Okay, so using this, we just convert this bound that we just derived in the KL divergence into a Wasserstein to distance. Okay, so now we want to bound the population loss, which is so we want to bound the expected value of f hat, where f hat is the true loss function minus the true minimizer of f hat. So this is the population loss.
F hat is the population.
I think this is.
And F is the empirical.
Yeah. So f hat is the expected value of fxs, where I sample s from the unknown distribution. So this is the population loss, and we upper bounded by these two terms. Again, this term is familiar to us. This comes from the excess empirical risk that we've seen before, whereas this term comes from the generalization gap, and we'll see how that comes. Okay, so this is the population loss, and note that we are sampling from pi d, which is this exponential in minus kf of xd. And again, I absorbed the regularizer term in f, so I assume that f itself is strongly convex. It's simplicity. Okay, so so I just replaced f hat x to be the expected value of the empirical function, and now exchange the order of the minimum and the expectation. So it's just a simple inequality. And we add this extra term and then subtract it. So now the first term, this term is something that we already seen. This is the excess empirical risk, and we know how to bound it by d by k. And the first term is what we want to prove bound. This is the generalization gap. So we are looking at the expected value of f hat x minus f of xd. So it's like the error that occurs because we are approximating f hat x by f of xd, which is what we have a handle on. So this is the generalization gap, and this is what we want to bound now. Okay. Yeah, even if you're not following exactly all the inequalities, but I just wanted to get the flavor of the bound. So generalization gap is this. So the first thing is this, clever step of converting this function, this gap. So this is an exact inequality here, exact equality. So we want to convert this generalization gap in the following form of it's just a difference between two loss functions at x and x prime, the same loss function at x and x prime, but now x is sampled from pi d and x prime is sampled from pi d prime, and d and d prime are two neighboring databases which are randomly chosen. So then this is an exact equality. So it's, yeah, I don't, unfortunately I don't I cannot convey a good intuition of how this manipulation works, but you have to believe me that you can rewrite this thing as exactly this. So it's just the difference of two loss functions. Sorry, the same loss function. When you plug in on one thing, you plug in x, which is output of the function on a database D, and x prime is the output of the function on D prime. So this is like M of D and M of D prime. And D prime are random neighboring databases. Okay, so now once we do this, we just apply the fact that f is G Lipschitz to get G times the L2 norm bound on x minus x prime. And we already seen that x and x prime, and we are bounded by the Wasserstein to distance here, because that is expected. You know, I can choose a coupling which minimizes this, and then I plug in the bound on the Wasserstein to distance that we obtain. Okay, so this is a kind of a stability bound. We are just saying that if D and D prime are neighboring databases, my algorithm will output two distributions which are close in Wasserstein to distance. Right.
What was your KL bound again? Like, do you need the Wasserstein?
So yeah, we need the Wasserstein to distance, right? Because ultimately we want to bound the L2 the L2 distance within x and the M of D and M of D prime. So we are converting the KL divergence bound. This is the KL divergence bound that we got. We're converting it into Wasserstein to distance bound. And that is what we want. We want to say that the output distributions are close in Wasserstein to distance.
Okay, I'll ask you more slowly.
Okay.
I'll ask you to go through it more slowly.
Okay, so basically that is the flavor of the proof. We showed that the output distribution should be close in Wasserstein to distance, and that immediately implies the generalization bound that we want, and we get the optimal population loss by plugging in the right K and U. Okay, so any questions so far? So now let's look at, I will not go into details of the algorithm of how we sample, but I'll just state the results. So, so what we show is that you can sample from exponential in minus f, and if we add the regularizer term, u norm of x squared by 2, and if G is G Lipschitz, we can sample from this distribution up to eta error in total variation distance in these many queries, G squared by mu queries. So, so the point to note is that the dependence on the dimension and the error is only logarithmic. Whereas previously all samplers either had polynomial dependence on the dimension or inverse polynomial dependence on the error, the total variation distance error. So here we get logarithmic in both, and the main constant is just these. It's a small number of queries. And in each query, you only need an unbiased access to F, an unbiased query to F. So if F is given as an expectation, then what you need is just a random Fi in each query. You don't need to query all the little Fi's in each step. Okay, so yeah, unfortunately, I don't have time to go into the details of the sampler. But then again, we show a matching lower bound saying that we need these many queries to sample from this distribution. So one open question is like, can we improve this using gradient queries? As I said, our sampler uses value queries. So what can we improve this bound using gradient queries? That would be interesting.
So just to, sorry, slow you down a little bit. So when you say there's polylog dependence on B, in the application that your main application, there is a dependence on D, but that comes through mu. Is that
that comes
through understanding?
Yeah, that dependence comes because we choose a really small mu there.
Yeah.
Okay, so yeah, so and then applying this algorithmic result, we can solve DPRM using n square queries to little Fi, and then the running time is a factor of D more. because each time you need to query, you need to give the point, which is of size d. And similarly, you can solve a DPSCO using these many queries, n times min of nd, and there's also matching lower bound, so that you need these many queries. Again, the open question that which is open is, can we do it using linear gradient queries? So if you see, like, if let's say n is smaller than d, or n is bigger than d, then the number of queries is n times d. So if it's a value query, each query is only giving a constant bits of information, whereas a gradient query uses d bits of information. So you can hope to get it with just n gradient queries. That is the interesting open question here. So to answer your question, Adam, if you all of this talk, I'm assuming that I'm not assuming any smoothness properties of f. But if you assume smoothness, you can get linear queries. But non-smooth, this is the best state of the art. So it's just a selection of algorithms, each with different multiples of n and d. Nothing achieves a linear anything. So this is the best known results using gradient queries. And the algorithms are all, like, again, complex, but it does a. Okay, so yeah, so this is the end of this part of the talk. Unfortunately, I don't have any more. I was also hoping to advertise our other result, but unfortunately, I don't have time. So I'll just give you the high level thing of this. Yeah. So the other result I wanted to advertise was, work on numerical composition of differential privacy. So, so what we give is a fast algorithm to compute the optimal privacy curve of composition to arbitrary accuracy. So if you give the privacy curves of each of the component algorithms, which is this delta as a function of epsilon, then it computes the delta as a function of epsilon of the composed algorithm optimally, which is like you cannot improve it. And it optimally, and then it computes it to arbitrary accuracy. And so here I gave an example of how it works for DPSGD. At the top, you can see that people typically use linear differential privacy to compute the privacy curves for DPSGD. Because DPSGD, there are like tens of thousands of steps that you need to compose the privacy of, and that green curve is the privacy curve that you can compute. But if you compute it using our PRV account, then optimally you can significantly reduce the epsilon by and that matters especially in practice where that's some 20-30% improvement in epsilon is or corresponding improvement in utility that you get. So yeah, so if you've been using linear differential privacy, I hope that you consider using this new accountant. There's a nice theoretical guarantee, which so take some time. But what we show is that if you have k algorithms, and let's say it's the same privacy guarantee, you can compose it in just square root k time, whereas the previous best bounds required k to the 1.5. So that is the algorithmic result. So it's quite fast, and it composes to arbitrary accuracy. So yeah, and with that.
But here the time bound depends on the epsilons you're computing.
Yes, so it's not the epsilon, it's the error. So the denominator is the error and the epsilon. So
okay.
So it's
the desired error.
Yeah, the desired error. And there is a logarithmic dependence on the error in delta. So which are both small. So for example, epsilon error, you can choose 0.1. Delta error is small. So, and anyway, it's a logarithmic dependence, so it doesn't affect too much. This epsilon upper is like the final upper bound on the epsilon of your final algorithm.
It's sort of a straightforward upper bound.
Yeah, it's a straightforward. You can use any upper bound. So that it's just so the better upper bound you can get, the faster our algorithm runs. Okay, so
but it's just like it's in the running time. So like if you're up to factor 2 or 3.
Yeah, it doesn't matter. So yeah, and then if it's the same algorithm that you're composing, it's just square root k time. So if you're composing like 100,000 algorithms, it just runs really fast.
So was the part of the theorem that also gives a better composition guarantee? Or is just about running time?
So the inner workings of it uses a different way to compose privacy guarantees. which is not by delta. So we introduced this thing called the privacy random variable, which composes better, which composes optimally. So that's what we use to get this theorem. Yeah. So yeah, it's an easy paper to read. So I urge you to read it. It's a different way to compose privacy guarantees than what is traditionally done. Yeah. And it gives you optimal privacy guarantees. And so we also did a comparison of running time to existing things. It runs like 1,000 times faster and to compute the same privacy guarantees. We also have a GitHub repo if you want to use. Yeah, thank you.
I actually have a question on when you measure the accuracy, you convert it to the from DL divergence or from KL divergence to the W2.
Yeah, W2.
And but you measure it on the W2, but when your mechanism design, it's an exponential mechanism, right?
Yeah.
And it can be it's not equivalent, but can be understood as a way of like adding noise based scales to the utility function's sensitivity.
Sensitivity of the utility.
It's like disturbing your results. It's not equivalent to adding noise, but it's also in a way to disturb the results, which scales to the function sensitivity. Because yeah, like does it make sense? No, I mean, so the exponential mechanism is also a way to disturbing the results, but the way to disturb the result is still need to scale to the function sensitivity, because when you design the mechanism, there is some parameters, which is
so the only parameter that matters is this k, which is like, so we sample from exponential minus k times the loss function. So
the loss function, there are sensitivity of this loss function, right?
Right. There is so we don't measure sensitivity of the loss. So the traditional analysis uses the sensitivity, which is the absolute bound that you can get on the loss functions.
Yeah.
But our analysis using just the Lipschitz property of this function. So these functions need not be bounded, or they will not have bounded sensitivity at all. So instead, we are using the fact that these are Lipschitz to argue that this is private. So the functions can be unbounded to themselves.
Okay.
So if the functions are themselves strongly convex, you don't need the domain to be that.
I see.
Okay. Like the case of the Gaussian Differential.
Yeah, I think my confused is like when you measure the unbounded sensitivity, you are using Lipschitz or other measurements. But when you measure the outcome, the accuracy, you are using a W2 distance. So I feel that the two measurements are different.
Maybe we can do this offline.
Okay.
And then better.
Okay. Sure.
Okay.